Hello everyone. Once again, I welcome you all on this in this lecture. This is the lecture number 13, and which is based on the ultrasonic machining. But just I want to brief you that in the last three lectures, 11, 10, 11, 12, we discuss about the abrasive jet machining. Okay, abrasive jet machining is just a combination of abrasive particles, or in other terms, we are defining that by the grit. Okay, and we are using a jet which is of air. Jet means we are using a very high velocity that is in the range of 150 meter per second to 300 meter per second. So that we are using a combination of that, and from that we are removing the material. So that we discuss about what is how the material removal is occurs actually when we are considering for both kind of material like brittle and the ductile. And we discuss some of the numerical problems as well. Okay, let's start with another machining process, advanced machining process, that is the ultrasonic machining process. So same process that I have already discussed with you before, that is a principle we discuss first, then we'll move to the working part, then we'll go to the how the material removal is actually takes place. And if there is any, like in this problem there are two objective problems is available, so that we will discuss. Okay guys, so let's start. Okay, so this is the ultrasonic machining. So as the name suggests that ultrasonic, this is nothing but a kind of frequency. Okay, ultrasonic frequency is a kind like we are working on just above the audible frequency. Audible frequency, that is in the range of like audible frequency I'm talking about, which is a range of 15 to 16 kilohertz. Okay, 15 to 16 kilohertz. Or if we are talking about like ultrasonic frequency, then that is in the range of 19 to 25 kilohertz. Or sometimes in some of the books it's mentioned 20 to 25 kilohertz. Okay, so that is basically the range of the frequency that we are using. But how we are using this frequency, that is important in this one. Okay, so let's start. Okay, so first one is we are going to discuss about the principle. So this is basically the workpiece, this one, bottom one. So actually it was the workpiece of this height. Okay, and after sometimes when the material is removed, that time this figure is shown. So this is the workpiece. Okay, this is the tool or tool tip, we can say. This is the horn, this is the part of horn, and horn, and about to this, this is connected with the transducers. Okay, so this is connected with the transducer, and this transducer is connected with the power supply. Okay, so this transducer is basically we are using here, this is a transducer we are using. Okay, this transducer we are using just to that we are using the ultrasonic frequency. Okay, so this frequency is generated by the transducer. Okay, then we are using the horn. Why we are using the horn, that I will tell you later on, but this is the horn. Okay, it's a long structure, kind of long shape, we can say, we are using. And the bottom of this horn we have connected the tool. Okay, or tool tip, we can say. So what is the principle is, principle is like this is the tool and this is the workpiece. So what we are doing is we are just passing a abrasive slurry. Abrasive slurry means again in the last abrasive jet machining we were using the abrasive slurry, but that abrasive slurry there is a combination of air plus abrasive grits. Okay, but here it is a, combination of water plus abrasive grits. So this abrasive slurry, the of water and the grit, abrasive grits, which is a combination of that, so that is passing through in between the workpiece and the tool. Okay, in between the workpiece and the tool, by passing from one side and another side is it coming out. So these abrasive particles, now we are using these abrasive particles. So these abrasive particles, when when we are initiating this frequency, so this is horn is vibrating, and horn, below to horn there is a tool is connected, so tool is also start vibration. Okay, so means vibrating. Okay, so this vibration is these abrasive particles. If we look just for 2 3 abrasive particle which is in a queue. So if you will see the top one, like there are three particles in which is just to contact, which is making a contact from tool to the tip. Okay, so these three abrasive particles, like first is this will vibrate, tool will vibrate, so the first particle will start also start vibrating. Is the second part, it is contact with the first one, so that will also start vibration, and third which is also in contact with the second one or the first one we can say, so that will also start vibrations, and third one which is at the contact of the workpiece, so is it will vibrate. It will vibrate means it will remove the material from the workpiece surface. Okay, so here this is basically the principle. We are using this ultrasonic frequency to remove the material. Okay, by scratching we can say. Okay, this abrasive particle which is vibrate over here, that is nothing but that's kind of scratch over the workpiece surface and remove the material. Okay guys, so and then we are using this abrasive slurry, so water is also there. So whatever the material that has been removed from the workpiece surface, that is just as we are continuously supplying this abrasive slurry, so whatever the abrasive particle, the material that has been removed from the workpiece area, that material is uh, because of this water, basically let flow of the water, that material which is removed, that also come along with the abrasive slurry only. Okay, so there we will discuss in the walking part. So this is how the actually the uh, principle, that is how the principle is takes place. Okay, means how the material removal is takes place in the ultrasonic machining. So what are the main important points are here. So machining process is applicable only for the brittle material. Yeah, this is important point. Why it is applicable for the brittle material only? That brittle material is hard. Okay, and harder material means whenever you will impinge, sorry, not impinge, whenever like you will scratch the hard material, they will basically try to start removing material from itself. But when we are talking about the ductile material, like just take an example of rubber. Okay, just take some kind of, just try to imagine that we have the emery paper, and there are two things. First is like a plate is there, brittle plate is there. Okay, a brittle steel, a mild steel plate is there, and just one side there is a rubber. Okay, simple rubber, that eraser we can say. So just try to just first just put a emery paper and scratch the mild steel plate. So some small amount of the material, that like we can say the powder in form, so that will start removing from that. Okay, so what we are doing, we are just scratching this. Now just make it, just do it on the rubber part. So in the rubber, it will not, like when you will try to scratch, it will, you will unable to move on that one. Why? Because this is the property of ductile material, that what it has a high uh, absorption energy. Okay, means toughness is very high. So if the toughness is very high, it means that whatever the force that we are applying, or the energy we are producing through the emery paper, that is completely absorbed by that material. Okay, so whatever the, because, and why I'm talking about this story means emery paper, because this is a kind of vibration. Okay, whatever the we are moving, rubbing over the workpiece surface, it means we are creating some kind of vibrations, means some amplitude is there. So whatever the these abrasive particles which is transferring vibrations from one to second to third one, in like that to the workpiece, so they will basically, it's a kind of scratch only. Okay, so they are removing the material by this scratch. Okay, so this, if we take an example of brittle material, then there will be a removal of the material by using this process. But if we take a, if we consider the example of ductile material, then there will be a no removal of the material. So that's because the amplitude which is generated by this ultrasonic frequency is also small. Okay, so that's why we cannot use this process for the ductile material. So please keep in mind, this is very important. So this process is applicable only for the brittle material. Okay, a tool of desired shape is vibrate at an ultrasonic frequency that is in the range of 19 to 25 kilohertz. Okay, guys, that I already told you. But in some of the books, it is mentioned like from 20 to 25 kilohertz. So there is no need to worry. This is just minute distance difference. Okay, with an amplitude of 15 to 50 micrometer over the workpiece. Now, guys, please, uh, this is very important. Let frequency is different and the amplitude is different. Okay, frequency at which this is transferred to the transducer, that vibrate the tool is vibrating. So that is basically the frequency. Okay, so that is in the range of 19 to 25 kilohertz. But is this tool is vibrating? Okay, this tool is vibrating, and it is like we can say, if it is vibrating, then this kind of things is happen. This kind of things means this is the tool, and there is another particle is there, so that is also start vibrating. The third one is that is also start vibrating. So this is a kind of vibrating. So how much, when it is from here to here, here to here, this is the amplitude. Okay, so this is the amplitude. So that is in the range of 15 to 50 micrometer. Please keep in mind this one. Okay, the machining portion, the machining portion is flooded with the hard abrasive water slurry. Okay, that I already told you. Once the frequency applied, tool start vibrations, and abrasive particles indent over the workpiece surface. Because of the indentation, cracks initiate. Now as I said that this is applicable only for the brittle material. So when like these abrasive particle will try to scratch that one, because that is a brittle material and very harder. Okay, because hardness is very high. So that will basically initiate the cracks. Okay, so now once the crack is initiated, is one single particle with, like just example, this is third particle which is in contact with the workpiece, that is initiated by the crack is initiated by that one. So other random particles are also there which is in contact with the third one. So if third will move, then another will come on that position. Okay, so that will, is they have a very already have a amplitudes, okay, or vibrating. So they will basically try to propagate that cracks. Okay, so initially because of the indentation, cracks initiate and propagate on the surface, causes the brittle fracture. Okay, so this is basically the principle how the material is removed in the USM process. Okay, ultrasonic machining process. So let's discuss the working part. Okay, so if okay, so this is basically the this is the high power supply. Okay, here this is the transducer portion, this is the transducer portion. And now this transducer portion is also like, this is a kind of mechanism is there. So this is mechanism is mechanism, and this is basically the servo mechanism. Okay, servo mechanism is like we have to feed it up and down. Okay, so this is the transducer which is connected with the horn. This is a horn, we can say. This is a transducer. So this is the transducer. Okay, this is the horn and this is the tool. Okay, now here this is the container. Okay, this is the container. Okay, and here this maroon color is basically the anvil. Over that fixture is mounted, and over the fixture, this red color is basically the workpiece. Okay, and if you will see this one, this is the water, and this black particles is nothing but the abrasive slurry. Okay, so here we are supplying this abrasive slurry up to here. Okay, by using the different kind of pumps. Okay, and so this abrasive slurry, which is a combination of water and the abrasive particles coming in contact with here, as we are passing through the hoses. So that is basically there is a gap is there, minimum gap is there between the tool and the workpiece. So in between it is flooded, and as we are switch on this power supply, transducer is used start vibrating. So that, because of that vibration, this horn start just it will modify this amplitude. Okay guys, so it will modify the amplitude, and that modified amplitude is transferred to the tool. Okay, so that will basically impinge over the, that will just not impinge, but that complete amplitude is or vibration is transferred to the abrasive particles which is in between the workpiece and the tool, and that will remove the material. So this is basically the working. Now here is we are using this servo mechanism. So the mechanism is like for an example, like if this is the workpiece. Okay, and this is the tool, and which is connected with the horn above that. Okay, so this is initially we are keeping this, and just assume that we are just this is flooded with the abrasive particles. So just for an example, like it takes some time to remove the material for 1 2 seconds or 3 seconds, something like that. So if for an example this much amount of the material has been removed during this time, okay, then what will happen now from here? If you will see, initially this was the distance. Okay, now this distance has been increased, and if you will see from this one, if you will see from this one nozzle tip to here, then this distance has been increased. Okay, initially this was this much only, now this has been increased from this much to this one. So is we want a constant distance. Why? Because if you will increase this distance, then number of particles initially, just for an example, that here only one or two particles were in contact between the workpiece and the tool. Now these particles will be flooded. Okay, so that number has been increased. So if this number will be increases, okay, this number of the abrasive particles or the distance between the workpiece and the tool is increases, then the whatever the vibration which is transferred to the tool tip, that is not exactly transferred to the workpiece surface. So what will happen, it will decreases the removal of the material, it will decreases the material removal rate. Okay guys, so please keep in mind this one. Okay, if you are not keeping this distance constant, then this will be decreases. Okay, so that's why what we are doing is, for that we are using the servo mechanism. Okay, so servo mechanism is, we are just noting down initially that how much time it is, for what, for an example, we have maintained some gap, and how much time is we are switch on the supplied, and that is working at the ultrasonic frequency. So how much time is taking to remove some specific amount of the material. Okay, so accordingly we are maintaining the speed of the anvil, sorry, this transducer which is connected with this mechanism. So accordingly we are feeding it towards the downside. Okay guys, so that is, we are just keeping a constant gap between the workpiece and the tool. Okay, so this is basically the working part. So feeding mechanism is provided to introduce the feed motion to the tool. Transducer used to generate the ultrasonic frequency. Okay, this is the transducer. And horn or connector is used to amplify the vibrations to the required amplitude, that is in the range of 15 to 150 microns, and accommodate the tool at its tip. Okay, this is the tool, sorry, this is the horn and this is the tool. Okay guys, so let's discuss about the power system and the types of the horn that we are using. So here, here these are the types of the different types of the horn that we are using. So a horn is nothing but like a, uh, uh, it's not, we cannot say it's a kind of prismatic bar, because according to the shape and size, because uh, like though, as I mentioned only these three, so it means that these three are suitable. Okay, and amplitude has been already measured. By the way, you can ask one more question here, that why we are not using a prismatic bar. Yeah, you can use, but by the different types of the horn that is mentioned in the books are on the basis of they have already measured. That's why they have given some specific kind of things. Okay, means that should be a taper in section, that should be a step wise, or that should be kind of curved section. So they have already measured the vibrations which is required, that is in the amplitude, that is in the range of 15 to 50 microns. So on the basis of that, which type of the horn is suitable. And it's not like what is that is also important here, is what is the diameter that you are maintaining with respect to the length. It's not randomly they have taken. Okay, this L by D ratio is also important. So accordingly they have said that these are the three types of the horn that you can use. So either you can use the stepwise or the taper section, or some kind of curve you can provide. Okay, so these are the suitable horns. Okay, let's discuss about the power system. So this is the signal generator. Okay, signal generator that is connected with the power amplifier. So this is the transducer which is connected to that, so that is producing the ultrasonic frequency, that is in the range of 19 to 25 kilohertz. Okay, so when, if you will see the vibration which is generated by this one, then it will look like okay. So if you will see the vibration which is generated by this one, then initially then there is no power supply, then this vibration is very small. Okay, means this vibration is only started, and this will be like this one. Okay, and as we have connected the horn, so this will be like increasing, and this will be like this much. Okay, so from this side also you can see like okay, so here you can see that amplitude. Okay, so this is initially the amplitude that is that produced by the transducer. Okay, and if you will maintain, because hardly what we have to do is we have to connect the tool over here. Okay, so this is the amplitude that we are getting over here. This is the maximum amplitude that we are getting, but as you will connect the horn, this amplitude is increases. Okay, this amplitude is increases, so that's why we are using the horn into that. Okay, and this is not like randomly we are using. By the experiment only, after the experiment only, we concluded something that okay, we can use the horn so that some specific length, it's not like infinite length we can use. Okay, it's not like that. So some specific length, at some specific length, up to that only this vibrations that is we are generated at this frequency, that is only be modified or being utilized. Okay, which is required. So this is the amplitude that is in the range of 15 to 50 microns, so that is generated. Okay, accordingly we are using these types of the horn, as well as what the workpiece is uh, what the workpiece means, what is the material of the workpiece, so accordingly we are using. Okay guys, so next is the modeling of material remote rate. So before starting just start about the material, I just want to brief about these terminology. So here is as the tool vibrates, it leads to the indentation of the abrasive grids. Okay, that we have already mentioned, that abrasive particle we are calling it here as a abrasive grid. Okay, hence primarily the material removal rate is occurs due to the indentation of the hard abrasive grids on the brittle work material. Okay, during indentation, crack propagates due to increase in stress and ultimately leads to the brittle fracture between the abrasive grids and the workpiece, that we have already discussed in the uh, working part. Okay guys, other than brittle failure, there is a solid impact erosion occurs due to free flowing of the impact of abrasive against the workpiece, but it is esteemed insignificant. Means this abrasive particle, like which is connected, which is due to the vibration, there is a crack is initiated and that is propagated. But as we are using the abrasive slurry, here we are using the abrasive slurry. So for an example, like if this kind of shape is formed and this is the tool. Okay, sorry, this is the tool that is, and these are the abrasive particles. So when these abrasive particle will flow along with the slurry, they will try to it will be like this shape is formed like this. Okay, because we are just assuming that these abrasive particles are moving in this direction along with the slurry, so they will remove some amount of the material from here as well as from here as well, but that is negligible. Okay, that is negligible. That is only the thing that is mentioned over here, that other than the brittle failure, solid to solid impact erosion. Okay, because this abrasive slurry is not like free fall, we are giving some velocity. Okay, so that speed is maintained, and that is occurs due to the free flowing of the impact of abrasive against the workpiece, but it is esteemed insignificant, means there is no meaning of that, means we cannot compare. Means large amount of the material wear is due to the brittle failure only. Okay, so let's model the material removal rate. But guys, here it's not that much like in the abrasive jet machining, we spent a lot of time on the material removal rate because some complex terms was there. So here we will not go for that much. Okay, no need to worry for you. No need to worry for that. Okay. So here is like same thing like that I already mentioned, that we are using this abrasive grit. Okay, abrasive grit is there. So what we are doing is as a first assumption, we are just considering it as a spherical in nature. Okay. So we are considering that average diameter, but now you can, here you can see that this is the abrasive, this is the tool. Okay, and this is the workpiece surface. So there are number of particles are there. Okay, number of abrasive particles are there. So what we are doing is we are just considering, because when this vibration is actually takes place, okay, this vibration is actually takes place, that time number of particles which is in contact with this surface area, and similarly which is in contact with the same, whatever the cross sectional area is here. Okay, the same cross sectional area will be here. So why I'm saying same cross sectional area, because in this cross sectional area, in this region, there are number of abrasive particles, there are number of abrasive particles. Okay, so these abrasive particles, because these abrasive particles is in contact with the tool, and when the tool is vibrating, these abrasive particle will start vibrating. Okay, and whatever the abrasive particle which is bottom to that, that will also start vibrating, and similarly happens. Okay, so because of the abrasive particle which is in contact with the workpiece surface, they will start try to remove the material. Okay, so what I want to say is there are not a single, we cannot say like a single abrasive particle is coming in contact with the workpiece and that is removing the material. Means at the same time there are number of abrasive particles. Okay, single particle is not there. So here one term is important, that is bulge. Okay, the bulge, bulge. Okay, bulge. So bulge is nothing but it is a combination of abrasive grids. Combination of abrasive grit, not grit, it's grits, abrasive grits. Okay, means we whatever the cross sectional area is there, according to it's like 10, 20, 30, 40, anything number, any number can be possible. So that is basically the number of grits. So if we are talking about the dimension, if for an example if I'm talking about that this is a bulge, okay, then it means that this is containing number of abrasive grids inside. Okay, please consider that one. Okay, so this is no doubt this diameter of this bulge is directly proportional to the dg, sorry, this is dg square. And if you will see proportional sign, if you will remove this one, this is mu equals to d, sorry, db equals to mu into dg square. So this is the relationship, that diameter of the bulge is equal to mu, that is some term is there, proportionality term is there, and that is equal to dg square. Now you can ask me one more term here, one question from here, that if this is db and this is dg square, how it can be possible? So guys, this is formulated, this formula is formulated or evaluated on the basis of experiments. So just you have to consider. Okay, do not point out here that dimensions. Okay, that's why we took the proportionality sign. Okay, so if it is in mm or centimeter, if it is in micron, so this is in mm square and this will be in per mm accordingly. Okay, so that will be satisfied both the sides. So do not consider that one. Okay, so this is like here we are considering that this circular one, or it's not circular, it's spherical in nature, exactly three dimension. So this is the diameter we are considering, and this diameter is equal to the db, that is the bulge diameter, that is db, that is bulge diameter. Okay, and this is the center of that, this is o point we are considering. Okay, and this is initially we are keeping, this is the workpiece. Okay, this is the workpiece surface. So after as it is impinging over the inside the workpiece, that time we are considering, because now we are talking about the bulge only, not about the grids. Okay guys, because that is a combination of that. Okay, so this abrasive bulge is coming in contact with the workpiece, and that is removing the material from this area, from this cross sectional area. Okay, so just we are considering that this is coming in contact it initially over here, and it is maintaining a constant radius, that is r. If it is a constant radius, then the this will be whatever the material that has been removed, that is spherical in nature. Spherical means if it is only inside the workpiece, so that is a semi sphere kind of things. Okay, so this is a semi sphere kind of things. Okay, so this is the semi-sphere, and this is the up to C. Okay, we can say that this is the maximum indentation. Okay, this is nothing but the delta. Okay, so now okay, let's make what is exactly the material removal rate will be. That material removal rate will be equals to what is general formula, that is how much amount of the material or the volume has been removed per unit time. Okay, so here we are considering the time terminology in the form of frequency. Okay, and frequency is like hertz we are defining, or kilohertz we are defining. So reciprocal of that, that is a time. Okay, so volume, how much volume of the material is removed from the workpiece area into the frequency. But here frequency is frequency is of ultrasonic frequency. But if we are talking about single frequency, it means that single bulge is in coming in contact with the workpiece, and sorry, single abrasive particle is coming in contact, and that is removing the material. But if we are talking about the bulge, then there are number of frequencies is there. Okay, number of abrasive grids is there, so they are vibrating at different amplitudes. Okay, so this is, that's why by the way, if we are talking about one grid, then that we can simply write f. but here we are not talking about one grid, we are talking about the bulge. So that is containing number of grids, abrasive grids. Okay, so that's why I'm writing n, and that is f is the frequency. So that is in hertz or kilohertz, accordingly we are taking. So this is the volume that has been removed from the workpiece. Okay, so if it is a semicircular in nature, if it is semicircular in nature, then how much amount of the material is removed from the workpiece area? So this volume will be equals to semi-sphere. Total volume of the sphere will be equals to 4 by 3 pi r cube. This is a semi-sphere, so this will be like 2 by 3 pi r cube. Okay, guys. So the material removal rate will be equals to 2 by 3 pi r cube into n into f. Okay, now is the same thing which we discussed in the last time, that these abrasive particles can be in different in nature, means different in dimensions. Okay, so if here we are considering that the bulge is containing 10 abrasive particles of different diameters, then in second times there is a possibility that it will be 8 grids only, like in next time it will be like 12 grids. So it can be increase or it can be decrease. Okay, so for that we have to calculate the indentation, because we can say like if one bulge is coming in contact with the workpiece and that is removing material, so we can say that this is the maximum. Okay, this is the maximum we can consider. So can we convert this term r in terms of delta? Yeah, obviously we can convert. Okay, so how we can convert that? If we are talking about this one, then this is what dB by 2. Okay, this is the radius of the bulge. Okay, and this will be like OB will be like BC will be equals to delta. This is the maximum indentation, and if we are talking about the OB, then this will be equals to dB by 2 minus delta. Okay, so now we have this triangle which is ABO. Okay, so this is ABO. Okay, so trying from triangle ABO. Okay, so just use, this is the 90 degrees, so just use the Pythagoras rule. So from the Pythagoras rule, hypotenuse square equals to, this is the hypotenuse will be equals to perpendicular plus base square. Okay, so hypotenuse square means OA square equals to OB square plus AB square. Okay, so OA square will be equals to dB by 2 whole square equals to OB square, that is dB by 2 minus delta square, plus AB is how much, that is R square. Okay, so this is dB square by 4, that is equals to dB square by 4 a minus b whole square, just I am opening that one, plus delta square minus 2 into dB by 2 into delta plus R square. Okay, so this is eliminated from both the sides. Delta is the indentation. Here we are considering the amplitude which is already in the like microns. Okay, so and this is the maximum amplitude only, so 50 microns. Okay, so microns, when you will go for a square, that will again become reduce the terms. Okay, so we are just eliminating this one, this will be equal to 0. So now here what is remaining, this from this one, so this will be like R square will be equals to, I'm just keeping this one, this term in the left hand side, so this will be like dB into delta, or if you want to calculate the value of R, then this will be equals to root square dB into delta. So this is the value of R. Okay, so just put the value over here. So from here the material removal rate, will be equals to 2 by 3 pi into dB into delta raised to 3 by 2 into n into f. Okay, so this is the material removal rate, and this is the material removal rate. There is no need to mention separately for the brittle material, because this process is only applicable for the brittle material, guys. Okay, so I hope that you understand this complete concept of the material removal rate. Okay, there are is if you will see here. Okay, then material removal rate, that depends on the bulge diameter. Okay, that how much diameter of the bulge is we are taking into consideration, as well as it depends on the frequency. Okay, delta also, it depends on the delta as well, but delta is actually depends on the how much diameter of the uh, bulge is there. Okay, so we are going to consider these two characteristics or the process parameter with respect to how it is affecting. So first I am considering the how this material removal rate is affected by the uh, diameter of the grid, we can say. Okay, diameter of the grid, we I already told you that this dB will be equals to mu into dg square, so there is no need to worry, or you can also write dB. Okay, and this is the material removal rate. Okay, so if we are talking about this one, then what will happen if we this is the material, this is the workpiece, and this is the sorry, this is the workpiece and this is the tool. Okay, this is the tool. So if we are if we are increasing the like for an example, if we are using a very small size abrasive particles. Okay, so just assume that because in alumina, in case of alumina, we can use maintain like 10 micron, 20 micron and the 50 microns. Okay, so let's suppose that 10 microns abrasive particles we are using. So whatever the space is there, if I'm just considering that into a single line or single column, we can say, then there are number of particles like 1 2 3 4 5 6 7. Okay, and if we are considering the 50 size, 50 micron size, then it will like just okay, so this is like here it's like 7 or 8 was there, but here only 5 or 6 is there. So the size has been reduced. Okay, so what will happen that why it is important, guys? Because this vibrations which is transferred to the tool, that is in the range of 15 to 50 microns only. This is also in very small in range. Okay, so this is the exactly the vibration which is needed, which is really required at the workpiece surface. But if you will see, then first, like just suppose that this 15 micron is transferred to this one, so this is in contact with the other one, second one, third one, fourth, fifth, sixth, seventh, like that. Okay, so they will reduce the amplitude which is really required at the workpiece surface. So what we are doing is we are increasing the size of that. Okay, so if we are increasing the size, then it's like now this amplitude has been increases. Okay, so if you are keeping this one, and also you can see that material removal rate is directly proportional to if we are keeping this delta and frequency constant, then this will be this will become dg raised to 3 by 2, this dg, sorry, db raised to db raised to 3 by 2, or in terms of, if I say this is, this is db raised to 3 by 2, or if you will see in terms of diameter of grid diameter, then when you will put mu into dg square, so this mrr will be equals to proportional to dg cube in terms of the grid diameter. So if for an example, if you are increase, let's assume that here it is a 1 in diameter, so the material removal rate will be like that. Okay, sorry, material removal rate will be like that. And if you are increasing this diameter from 2, then 2 then it will become 8. Okay, because it's a cube. When you will become 3, it will become 27. When you will become 4, it will become means it is continuously increasing. Okay, so this curve will be like this, means steepest towards the material removal rate side. Okay, this axis side. Okay, so this will be like that. And is you are increasing the dimensions of this abrasive particles, like just assume that now you are using only single grid. Okay, fine, that will be but vibration is it's this vibration is not exactly between the ductile material, so that it will like jump. Okay, this abrasive particle will be jump, it's not like that. Okay, this is between the brittle material, so a minimum shape will be required, okay, to retain these vibrations, these retain this amplitude. But now you are just assume that we are using only one abrasive particles, so as you will transfer these vibrations to the single grid. Okay, then it do not have the space to vibrate. Okay, or let's assume that you are increasing the dimension of that this abrasive grid, now this one only. So this abrasive grid is coming in only this much contact of the workpiece surface, oh sorry, tool. So how much amount of the amplitude that will transfer to the workpiece? Okay, very negligible. So what is the meaning is, as you increase the grid diameter, the material removal rate is increases, but after some times, after the optimum value, after reaching the optimum value, it is start decreasing. Okay, so this is the optimum value of this dg at which the material removal rate is maximum. This is the optimum value at which the material removal rate is maximum. After that, it will start decreasing. Okay, guys. So please keep in mind this one. Now, there is one more thing is there. Okay, this is second one is the material removal rate with respect to the frequency. So this is nothing but you can directly get it from this relationship from this one, that this if we are keeping this bulge or the grid diameter constant and delta is constant with respect to the bulge diameter. So this is only dependent on the frequency. So the here from here the material removal rate will be directly proportional to the frequency. So if you will see the curve, then it will be like a straight line. Okay, this will be a like straight line. So this is the minimum value, like we can say like 19 kilohertz. This is the maximum value of 25 kilohertz. Okay, so up to that we can say that that will be a straight line. Okay, guys, so this is the material removal rate with respect to the frequency. Okay, uh, fine. So just two objective problem I'm taking. After that, I will end this session. So first is like in USM, the material removal rate would fill in the blank with increasing mean grain diameter. Grain diameter means grid diameter only we are talking about here. Okay, diameter of the abrasive particles. So first option is increases when the material what the meaning is. This question was asked in GATE mechanical 1992. Okay, so what the question is like, how the material removal rate will be affected by the grid size. If here it's mentioned that if, when we are increasing the grid diameter, then what will happen. Okay, when we are increasing the grid diameter for the some time being, it is increases. Okay, we can say that if it is mentioned that for the time being, for the optimum value, till the optimum value of the grain diameter, if we are increasing, then obviously it is increases. Obviously it is increases, but that is up to the optimum value only. So this here, it's in the question, it's not mentioned optimum value. So please, this answer is not correct. Okay, as you are increasing the size, it is the material removal rate is decreases. This is completely wrong. So these two options are already eliminated, B and D. So now the option only C is remaining. First it is increases, then after some times at the optimum value it start decreasing. So the option will be C. Please keep in mind. Okay. The next question is in an ultrasonic machining process, the material removal rate will be higher for the material width. Okay, the material removal rate will be higher for the which here it's a property or a material with respect to the material is given to you. So first is high toughness. If it is the high toughness, then obviously it will be a ductile material. We can simply take example of the rubber. So if as I already mentioned that this process is not at all applicable for the ductile material, so this option is eliminated. Okay, high ductility, obviously the materials which have a high toughness, they have only high ductility, so this also be eliminated. High fracture strain, so this is like if we are increasing the toughness, then the fracture strength is also increases accordingly. So that is also eliminated, only the lower toughness. So it has a, in other words we can say that it has a high hardness. Okay, high hardness, and the meaning of that high hardness is the brittle material. Okay, so the ultrasonic machining process, the material removal rate will be higher for the material which is with the lower toughness. Okay, so guys, please keep in mind this one. So thank you so much guys for this session. We'll discuss the LBM and the EBM process in the next lecture. Okay, so thank you so much.